Hello everyone. Welcome to today's presentation. I'm excited to have you here. The topic we'll be exploring is called CIRCLES. This is the very first slide, so I want to give you a quick overview of what's ahead. We'll be diving into the fascinating world of circles, their properties, and why they matter. We'll cover some key concepts and see how circles appear in everyday life. But for now, let's get started and enjoy the journey. Let's take a look at some important points to remember about circles. First, we'll start with an introduction to circles, which are fundamental in understanding many geometric concepts. For example, in exercise 10.2, you'll see practical applications of what we're discussing. Next, we'll explore key elements like chords, tangents, and secants. These are essential for understanding how circles interact with lines. Did you know that at most, 2 parallel tangents can touch a circle for a given secant? That's a fascinating property that we'll clarify further. We'll also review important terms related to circles, so you're familiar with the vocabulary used in this topic. When it comes to the length of a tangent, there are specific formulas and properties that help us measure and understand these segments. Remember, there are several crucial points to keep in mind, especially regarding how tangents and secants behave and relate to each other. For example, from an external point, a tangent can be drawn to a circle, and understanding this helps in solving many problems. Finally, we'll see some real-world applications of circles in daily life, demonstrating how these concepts are not just theoretical, but also practical. All these points together form the foundation for a solid understanding of circles, so let's keep these key ideas in mind as we move forward. You can draw a circle using a compass, which is a handy tool for creating perfect circles. Now, the distance from the center of the circle to its edge, or circumference, is called the radius. Think of it as a line that stretches from the middle of the circle out to its boundary. The circumference itself is the set of all points that are at a fixed distance from the center, forming the boundary line of the circle. In fact, a circle is basically a collection of all those points in a plane that are at a constant distance, known as the radius, from a fixed point called the center. So, when we talk about a circle, we're referring to this entire set of points that are evenly spaced at that same radius around the center point. And so, what exactly is a circle? It's a shape defined by this perfect symmetry of points at a fixed distance from a central point. This concept is fundamental in understanding many geometric principles we'll explore later, especially how circles relate to other shapes and measurements. Let's explore some real-life applications of circles that we encounter every day. Circles are everywhere around us, from the wheels on our vehicles to the shape of coins we use. They play a crucial role in engineering and design because of their perfect symmetry and uniformity. For example, when we think about clocks, the face of a clock is a circle, and the hands rotate around its center, making it a perfect example of how circles help us measure time. Similarly, gears and pulleys rely on circular shapes to transfer motion smoothly and efficiently. Even in nature, we see circles in ripples on water or the cross-section of tree trunks. Connecting this to our overall theme, understanding how circles function in daily life helps us appreciate their importance in technology, design, and nature, making our lives more efficient and interconnected. Let's explore some important terms related to circles. First, an arc is simply a continuous part of the circumference of a circle. Think of it as a slice of the circle's edge. Next, when we draw a chord, it divides the circle into 2 segments. The smaller of these is called the minor segment, while the larger one is called the major segment. Moving on, the diameter is the longest chord in a circle, passing through the center and touching 2 points on the circumference. Lastly, a sector is the region between an arc and the center of the circle, kind of like a slice of pizza. These concepts are fundamental because they help us understand and analyze the different parts and properties of circles, which is a key theme in our overall study. Let's explore the different ways a line can relate to a circle on a plane. First, if the line PQ intersects the circle at 2 distinct points, A and B, we call that line a secant of the circle. The segment OB, which connects these 2 points, is known as a chord of the circle. Next, if the line PQ touches the circle at exactly 1 point, we say that PQ is a tangent to the circle. This is a special case where the line just grazes the circle without crossing inside. Lastly, if the line PQ does not intersect the circle at all, meaning it has no points in common with the circle, we refer to it as a non-intersecting line. These three possibilities, secant, tangent, and non-intersecting, cover all the ways a line can relate to a circle on a plane, helping us understand the fundamental concepts of circle geometry as we move forward. All right, let's dive into the concept of tangents. So, when we talk about a tangent to a circle, we're referring to a line that touches the circle at exactly one point. That point is what we call the point of contact, which we're denoting as A now. An interesting fact is that for every point on the circle, there is a unique tangent that passes through it. This means that at any point along the circle, there's only one line that just touches it and doesn't cross through. This property helps us understand how tangents behave in relation to circles, and it's fundamental in many geometric proofs and constructions. Remember, the key takeaway here is that a tangent touches the circle at exactly one point, and for each point on the circle, there's a unique tangent passing through it. Now let's talk about the secant of a circle. PQ here represents a secant, which is a line that intersects the circle at 2 points. When it does so, it forms a chord of the circle, which is simply a segment connecting those 2 points on the circle. A key thing to remember is that a secant has 2 distinct points in common with the circle, unlike a tangent, which just touches at 1 point. So, in essence, a secant cuts through the circle, creating a chord, and this concept is fundamental when studying the relationships between lines and circles in geometry. Now, let's explore an interesting property of circles involving secants and tangents. For every given secant of a circle, there are exactly 2 tangents that are parallel to it. These tangents touch the circle at 2 points that are diametrically opposite. What does this mean? Well, if you imagine drawing a secant line passing through the circle, there will always be 2 specific tangent lines that run parallel to this secant. These tangents don't just touch the circle at any random points. Instead, they contact the circle at points that are directly opposite each other across the circle's center. This concept highlights a beautiful symmetry in circle geometry. It also ties into the overall theme of how lines relate to circles, especially how parallelism and symmetry play crucial roles in understanding geometric properties. So, in essence, for any secant you choose, you can identify exactly 2 parallel tangents, each touching the circle at opposite points, demonstrating the elegance and consistency in circle geometry. When a point of tangency lies on the circle, there is exactly 1 tangent to the circle that passes through it. This is a key concept because it highlights the uniqueness of that tangent line at the point of contact. On the other hand, if the point is inside the circle, any line you draw through that point will be a secant, meaning it will intersect the circle at 2 points. So, in this case, you cannot draw a tangent that passes through a point inside the circle, because a tangent touches the circle at only 1 point, and that point must be on the circle itself. Now, considering the number of tangents you can draw from a given point, whether it's outside the circle, on the circle, or inside, it's important to remember these key distinctions. This understanding is crucial because it ties into the overall theme of how lines interact with circles, and it helps us visualize possible lines and their properties depending on where the point is located relative to the circle. When the point lies outside of the circle, there are exactly 2 tangents that can be drawn to the circle through that point. This is a fundamental concept in geometry because it shows how external points relate to circles. These tangents are unique lines that touch the circle at only 1 point each. It's important to remember that these 2 tangents are always equal in length, which is a key property. This idea connects to the overall theme of how lines and points interact with curves like circles. Understanding this helps us grasp more complex geometric principles and their applications. The length of the tangent from the point, which we'll call P, to the circle is actually defined as the segment that runs from the external point P all the way to the point of tangency I on the circle. In simple terms, you can think of it as the straight line segment that touches the circle at exactly 1 point without crossing it. In this case, The length of this tangent segment, from P to I, is what we refer to as the tangent length. Understanding this concept is key because it helps us analyze distances and angles involving tangents, which are fundamental in many geometric problems. This idea also ties into the overall theme of the presentation, which is about understanding how lines interact with circles and how certain lengths and angles are related in these configurations. Let's now explore the concepts of chord, tangent, and secant. These are fundamental in understanding how lines interact with circles. A chord is simply a line segment that connects 2 points on the circle's circumference. It divides the circle into 2 parts and is crucial in many geometric properties. Next, we have the tangent. A tangent touches the circle at exactly 1 point, which we call the point of tangency. It's unique because it only intersects the circle at this single point, and the line is perpendicular to the radius at that point. This perpendicularity is key to many proofs and properties involving circles. Finally, the secant is a line that passes through the circle at 2 points, effectively intersecting the circle in 2 places. Secants extend beyond the circle, but their segment between the 2 intersection points is often called a secant segment. Understanding these lines and their relationships helps us analyze angles, lengths, and other properties related to circles. They form the basis for many theorems and problem-solving strategies in circle geometry, connecting to the overall theme of understanding shapes and their properties. Let's take a closer look at the circle. This diagram is really useful for understanding how different concepts or components are interconnected. The key here is to see the circle as a representation of continuous flow or ongoing processes. Notice how each segment relates to the others. It's not just isolated parts, but a dynamic system where each piece influences the next. This interconnectedness highlights the importance of looking at the bigger picture rather than just focusing on individual elements. By understanding the relationships within the circle, we can better grasp how to optimize the entire system or process. In the context of our overall theme, this circle reminds us that success often depends on maintaining balance and harmony among all parts. So, when we think about solutions or improvements, it's crucial to consider how changes in one area might ripple through the entire circle. Today, let's focus on some key properties of tangents to a circle. First, note that at any given point on a circle, only one tangent can be drawn. This means that from a specific point on the circle, there's a unique line that just touches the circle at that point without crossing it. Next, consider an external point outside the circle. If we draw 2 tangents from this point to the circle, an interesting fact is that these 2 tangent lengths are always equal. This is a fundamental property that helps us understand the symmetry involved. Now, moving to the equal tangent LENGTHS theorem, which states that if you draw a line through the endpoint of a radius and make it perpendicular to that radius, this line will be a tangent to the circle. This is a handy way to construct a tangent line if you know the radius. Let's also clarify what we mean by the point of contact. It's simply the point where the tangent touches the circle, and this point is called the point of contact. Understanding this helps us see how the tangent and the circle are related at that specific spot. Finally, the tangent radius theorem tells us that the tangent at any point on a circle is always perpendicular to the radius drawn to that point. This perpendicularity is a key concept that links the tangent line and the radius, reinforcing their special relationship. Remember these points. They form the foundation for understanding tangents and their properties in circle geometry. Let's explore some important concepts about tangents and circles. First, the point where a tangent touches the circle is called the point of contact. This is the exact spot where the tangent intersects the circle. Next, a circle can have at most 2 parallel tangents. Think about it, if there were more, they would eventually intersect or overlap, which isn't possible for parallel tangents. Moving on, a line that cuts through a circle in 2 distinct points is known as a secant. It's like a line passing through the circle, creating 2 intersection points. Lastly, a tangent to a circle touches it at exactly 1 point, which we call the point of contact. Now, here's an interesting fact. Since a circle has infinitely many points on its circumference, it can have infinitely many tangents, one at each point. So, how many tangents can a circle have? The answer is infinitely many. This highlights the richness of the circle's geometry and how these tangent concepts connect to the larger theme of understanding circle properties. Let's look at this interesting geometric setup. We have two lines, OB and XY, which are parallel to each other. The line OB is tangent to the circle at point C, meaning it just touches the circle at that single point. Meanwhile, XY acts as a secant line, meaning it passes through the circle, intersecting it at 2 points. Now imagine drawing this circle and these two lines. Remember, the tangent line OB touches the circle exactly at 1 point, C, without crossing it. The secant line XY cuts through the circle, creating 2 intersection points. This configuration is fundamental in understanding properties of tangents and secants, especially how they relate to the circle's center and radius. Moving on to the problem, the key point is to find the length PQ, which is a segment related to the tangent and secant. The correct answer here is option D, which is the square root of 119 centimeters. How do we arrive at this? Well, by applying the Pythagorean theorem, we analyze the right triangle formed by the radius and the segments involved. Specifically, we find that PQ squared equals 119, which comes from subtracting 25 from 144. These are the squares of certain lengths involved in the setup. Then, using the relationship between the distances from the center to points Q and P, and applying Pythagoras in triangle OPQ, we establish the perpendicularity between OP and PQ, meaning OP is perpendicular to PQ. This perpendicularity is crucial because it confirms that the line drawn from the center O to the tangent point P is perpendicular to the tangent line itself. That's a fundamental property of tangents in circle geometry. Finally, considering the given lengths, we see that OQ equals 12 centimeters, and the radius of the circle is 5 centimeters. Using this information, we can determine the length PQ, which turns out to be square root 119 centimeters, matching choice D. So, the key takeaway here is understanding how tangent and secant lines relate to the circle's radius and center, and how the Pythagorean theorem helps us find unknown lengths in these configurations. Let's analyze option A, which states that the radius of the given circle is 7 centimeters. This means that OP, the distance from the center O to the point P on the circle, equals 7 centimeters. Therefore, we can write OP equals 7 centimeters. Squaring both sides, we get OP squared equals 49. Next, using the given information, we see that OP squared is also equal to 625 minus 576, which simplifies to 49, confirming our earlier calculation. Moving forward, applying the Pythagorean theorem in triangle OPQ, we find that OQ squared equals OP squared plus PQ squared. Since we have OP squared as 49 and PQ as 24, OQ becomes the square root of 25 squared, which is 25 centimeters, and PQ is 24 centimeters. From the figure, it's evident that triangle OPQ is a right-angled triangle. This is important because it confirms that OP is perpendicular to PQ, meaning OP is perpendicular to the tangent at point P on the circle. To visualize this further, imagine drawing a perpendicular line from the center, O, directly to the point P on the circle where the tangent touches. This line will be perpendicular to the tangent line, reinforcing the right-angle relationship. Finally, considering the options given, 7, 12, 15, and 24.5 centimeters, we're asked to find the radius of the circle. Given our calculations, the radius is clearly 7 centimeters, which matches option A. Remember, in circle geometry, the key concepts involve understanding distances from the center, the properties of right triangles formed with the radius and tangent, and applying the Pythagorean theorem accurately. These are the core ideas that help us solve such problems efficiently. Let's examine the key angles involved here. We have that angle PTQ is 70 degrees, which corresponds to option B now. Notice how we add the angles. PTQ plus 90 degrees, then 110 degrees, and another 90 degrees, summing up to 360 degrees. This is because these angles form a complete circle around the point. Next, by substituting the specific values, we see that the sum of the angles PTQ, POC, OPT, and OCT also equals 360 degrees. This makes sense because they are angles around a point, and the total around a point is always 360 degrees. Now, focusing on the quadrilateral POQT, we know that the sum of its interior angles is 360 degrees. From this, we can deduce that OPT and OCT are both right angles, so each measures 90 degrees. This leads us to the important conclusion that OP is perpendicular to PT, and similarly, TQ is perpendicular to OQ. Recognizing these perpendicularities helps us understand the geometric relationships better. From the question, it's also clear that OP and OQ are radii of the circle, because they are perpendicular to the tangents PT and TQ, respectively. This is a crucial point since it connects the properties of the circle with the tangent lines. Finally, considering all this, the key takeaway is how the angles and perpendicularities relate to find the measure of PTQ. And with all the given information, the correct answer to the question is 70 degrees, which matches option B. Now, let's explore how to find POA. First, note that OA is perpendicular to PA, and OB is perpendicular to PB, which we establish using the tangent radius theorem. This is a key point because it helps us understand the right angles involved. Option A is the correct choice here, leading us to conclude that POA equals 50 degrees. From there, we observe that twice POA gives us 100 degrees. Next, by substituting the known values, we find that 2 times POA equals AOB, which means AOB is 100 degrees. We also see that AOB equals the sum of POA and POB. Given that AB is 80 degrees, and because of CPCT, corresponding parts of congruent triangles, POB equals POA. This makes sense since OB is the radius to tangent PB. Now, considering triangles OPB and OPA, we see they are congruent by SSS, side, side, side. Because OP is common, OA equals OB as radii, and AP equals BP since tangents from a common point are equal. From this, we confirm that AOB is 100 degrees. Then, adding this to 260 degrees, we reach a total of 360 degrees, which makes sense because we're summing angles around a point. In the quadrilateral AOBP, we find that OB and OP are both 90 degrees since OA is the radius to tangent PA, and similar reasoning applies to PB. Finally, the question asks, if tangents PA and PB from point P to the circle are inclined at 80 degrees, then POA must be 50 degrees, which aligns with option A. This thorough analysis links all these geometric concepts together, helping us understand how angles relate in circle tangent configurations. So, as we can see, the proof shows that the tangents drawn at the ends of a diameter are indeed parallel. From the figure, we observe that OB equals OC because they are alternate interior angles. Similarly, OBS equals OP for the same reason. Since alternate interior angles are equal, this implies that lines PQ and RS must be parallel. Now, an important point here is the tangent radius theorem, which tells us that the radius of a circle drawn to a point of tangency is perpendicular to the tangent line at that point. Therefore, OB is perpendicular to RS, and OA is perpendicular to PQ. Consequently, the angles OBR, OBS, OP, and OC are all 90 degrees. In this setup, with 2 tangents drawn at points A and B, and OB being the diameter, the perpendicularity of radii to tangents confirms that the tangents at the ends of the diameter are parallel. This aligns perfectly with the overall theme of understanding the properties of circles and tangents, illustrating how these geometric principles come together to prove such a fundamental fact. Now let's look at this key concept. The perpendicular at the point of contact to the tangent actually passes through the center of the circle. To understand this, consider the angles involved. We see that angle XBB is equal to angle OPB, which tells us something important, that these two angles can only be equal if the points O and X coincide. Essentially, this means the point X and the center O are the same point. Next, from earlier statements, we know that OB is perpendicular to PX, which makes angle XBB a right angle 90 degrees. This is what we refer to as statement 2. On the other hand, by the way we've constructed our diagram, the radius OP is perpendicular to the tangent OB at point P, which gives us that angle OPB is also 90 degrees. That's statement 1. Now remember, the tangent to a circle at any point is always perpendicular to the radius drawn to that point. So, if we join the center O to P, this line OP, it forms a right angle with the tangent OB at P. To make sure we understand this thoroughly, let's consider a proof by contradiction. Suppose PX does not pass through O. Our goal is to prove that PX actually does pass through O. Assume, for the sake of argument, that PX is perpendicular to OB at P, and that the tangent OB touches the circle at P with center O. In essence, what we're showing is that the perpendicular at the point of contact must go through the center O, which aligns with our understanding of the properties of a circle and its tangents. This is a fundamental idea in circle geometry, and it's crucial for developing further concepts in the overall presentation. So, from the previous steps, we see that the radius of the circle is 3 centimeters. This means that OT, which is a radius, is equal to 3. Next, we look at OT squared, which is 3 squared, giving us 9. We also see that this can be expressed as the product of 1 and 9, which equals 9, confirming our radius length. Then, we observe that OT squared can also be written as the product of 5 minus 4 and 5 plus 4. This is a clever way of expressing the difference of squares. Simplifying, 5 minus 4 times 5 plus 4 equals 5 squared minus 4 squared, which is a classic identity. And since 5 squared is 25 and 4 squared is 16, their difference is 9, matching OT squared. Furthermore, we see that 5 squared equals OT squared plus 4 squared. This is a key relationship in right triangles, specifically the Pythagorean theorem. In the same vein, OP squared equals OT squared plus PT squared, which again is an application of the Pythagorean theorem, since we're dealing with a right triangle here. Now, looking at the right triangle delta OTA, we recognize that angle OTA is 90 degrees, which confirms the right angle at T. And, as a key point, remember that the tangent to a circle at a point is always perpendicular to the radius drawn to that point. This is a fundamental property that underpins many problems involving tangents. Finally, to illustrate this concept, there's a question. If the length of a tangent from a point A, which is 5 centimeters away from the circle's center, is 4 centimeters, what is the radius of the circle? This type of problem helps us see how the relationships we've discussed come together to solve real-world questions involving circles and tangents. Hence, the required length of the chord OB is 8 centimeters. From this, we find that AP equals 4 centimeters. Now, looking at AP squared, we see it equals 16, which is 4 squared. We can also express AP squared as the product of 5 minus 3 and 5 plus 3, which simplifies to 2 multiplied by 8. Alternatively, AP squared equals 5 squared minus 3 squared. Rearranging this, we get 5 squared equals AP squared minus 3 squared. Moving on, in the right triangle APO, we observe that OA squared equals AP squared minus OP squared. Now, focusing on the geometry in the figure, O is the common center of the two concentric circles. Let's consider the key relationships. Since AP equals BP, the total length of OB is the sum of AP and BP. An important point to remember is that a radius perpendicular to a chord bisects that chord. Therefore, OP is 90 degrees, which tells us that OP is perpendicular to OB, according to the tangent radius theorem. Since OP is the radius of the smaller circle passing through P, the point of contact, OB acts as a chord of the larger circle, and it's tangent to the smaller circle at P. To sum up, in this configuration, O is the common center, and the goal is to find the length of the chord of the larger circle that touches the smaller circle. This example illustrates how understanding the relationships between radii, chords, and tangent points helps us solve such problems effectively. So here we see that the key relationship is that AB plus CD equals AD plus BC. This is a fundamental property of a tangential quadrilateral, which is what we're dealing with here. Now, moving further, we consider the extended equations involving the segments doctor, AP, BP, CR, DS, AS, BQ, and CQ. By analyzing the figure, we observe that, thanks to the equal tangent lengths theorem, certain pairs of tangents from an external point to a circle are equal. For example, doctor equals DS because they are tangents from point D similarly, AP equals AS, BQ equals BP, and CQ equals CR. These equalities are crucial because they allow us to pair up segments and simplify the relationships. The main idea here is that since the sides AB, BC, CD, and DA touch the circle at points P, Q, R, and S respectively, the lengths of the tangents drawn from each external point to the circle are equal. This property is what enables us to establish the equality of sums like AB plus CD and AD plus BC. In essence, this proof hinges on understanding that the lengths of two tangents drawn from an external point to a circle are equal, and that this property, combined with the configuration of the quadrilateral, leads us directly to the conclusion that AB plus CD equals AD plus BC. This is a beautiful illustration of how tangent properties and geometric relationships work hand in hand to reveal these elegant equalities. Let's analyze this step by step. First, we establish that angle AOB is 90 degrees. This is a crucial point because it tells us that the angle subtended by the diameter at the circumference is a right angle. Next, we see that twice angle COA plus twice angle COB equals 180 degrees, which comes from the properties of angles in a circle. From these equations, we can deduce that the sum of angles POA, COA, COB, and QOB equals 180 degrees. Remember, POQ is a diameter, so it forms a straight line, which is fundamental in our reasoning here. It helps us understand the relationships between the various angles involved. Now, considering the triangles OQB and OCB, we find they are congruent by the criteria of SSS, side, side, side. This congruence leads us to conclude that angles QOB and COB are equal, which is a key insight for our proof. Similarly, the triangles OPA and OCA are congruent, again by SSS. This congruence allows us to establish that AP equals AC, since these are tangents from point A, and that AO equals AO, which is simply the common side. Further, in triangles OPA and OCA, because their sides are equal as established, OP equals OC, both being radii of the same circle, we can see that the angles involved are also equal, reinforcing our previous conclusions. In the figure, we have two parallel tangents XY and XI with a center O, and another tangent OB touching the circle at point C, intersecting XY at A and XI at B. The goal is to prove that angle AOB equals 90 degrees, which ties back to our initial statement and the overall theme of circle geometry and tangents. Throughout this proof, the key takeaway is how properties like congruence, angles in a circle, and the nature of tangents all interconnect to demonstrate that the angle between the two lines from A to B is a right angle. This understanding is fundamental when working with circle theorems and tangent properties. So, here we see that the angle between the two tangents drawn from an external point to a circle is actually supplementary to the angle that's subtended by the line segment joining the points of contact at the center. In other words, the sum of the angles AP and BOA equals 180 degrees. Now, if we consider the full circle around point O, we know that the angles around a point sum up to 360 degrees. So, adding 90 degrees to each of these angles, we get a total of 360 degrees. From this, we can deduce that the sum of the four angles, OP, AP, PBO, and BOA, must also be 360 degrees. This is a key idea because it ties together the angles at the points of contact and the center, showing how they complement each other within the circle. In the quadrilateral formed by points O, A, P, and B, we observe that OB is perpendicular to PB, which means OB is a right angle, or 90 degrees. Additionally, OB is the segment that joins the contact points A and B, and it subtends the angle AOB at the center O. Furthermore, since OA is perpendicular to PA, the angle OP must also be 90 degrees. This helps us understand the relationships between the tangents, the contact points, and the center, reinforcing the geometric connections in this configuration. Finally, when P is an external point from which the tangents PA and PB are drawn, these tangents touch the circle at A and B respectively. The key takeaway here is that the angle between these two tangents is directly related to the angle subtended by the line segment OB at the center O, and as we've shown, these angles are supplementary, meaning their sum is 180 degrees. This result beautifully ties together the properties of tangents, contact points, and the circle's center in a comprehensive way. Let's analyze this step by step. First, we see that OB equals BC, which equals CD, and that equals DA. From this, we conclude that ABCD is a rhombus. Now, by comparing equations I, Roman 2, and Roman 4, we find that OB equals BC. Multiplying both sides by 2, we get 2 OB equals 2 BC. Next, substituting from equations I and Roman 2, we see that OB plus CD equals AD plus BC. This leads us to the key point that the sum of certain tangent segments, specifically Dr plus CR plus BP plus AP, equals the sum of DS plus CQ plus BQ plus AS. Rearranging, we find that Dr plus CR plus BP plus AP equals DS plus CQ plus BQ plus AS. Now, if we add all these segments, we observe that AP equals AS because they are tangents to the circle at A, and similarly, BP equals BQ, CR equals CQ, and Dr equals DS, since these are tangents at the respective points. This is based on the tangent length theorem, which tells us that tangents from a common point to a circle are equal. From there, considering the figure, we see that BC equals AD, which confirms that opposite sides are equal. Since ABCD is a parallelogram with equal opposite sides, and we have all these tangent segment equalities, it follows that the parallelogram circumscribing a circle must be a rhombus. So the key takeaway here is that the properties of tangents and equal segments, combined with the parallelogram's characteristics, lead us to conclude that such a figure is a rhombus. This ties back to the broader theme of how circle properties influence the shape of polygons inscribed or circumscribed around them. Let's analyze the given information step by step. We start with the segments OB and AC. We find that OB equals x plus 8, which simplifies to 7 plus 8, giving us 15 centimeters. Similarly, AC equals 6 plus x, which simplifies to 6 plus 7, resulting in 13 centimeters. From this, we deduce that x equals 7 centimeters. Next, we see the equation 32x equals 224, which confirms our value for x. We then proceed to manipulate the equations to relate the segments and the area of the triangle. For instance, 48x equals 224 plus 16x, which simplifies to 48x equals 16 times 14 plus x multiplying out. We get 48x times 14 plus x equals the square of 56 plus 4x, and so on. By squaring both sides, we derive an expression involving the square root of 14 plus x multiplied by 48x, which equals 56 plus 4x. This step is crucial because it allows us to connect the segments to the area of the triangle. Furthermore, we see the use of Heron's formula, where the area of triangle ABC is expressed as the square root of the semiperimeter S times S minus each side. We find that the semiperimeter S equals 14 plus x, based on the sum of the sides divided by 2. Connecting all these points, we recognize that the lengths of the tangents from a common point to the circle are equal. So CF equals CD, both 6 cm, and B equals BD, both 8 cm. These equal tangents help us determine the segments on the sides. Finally, with all these relationships established, The goal is to find the lengths of sides OB and AC, given the constraints of the circle with radius 4 cm and the division of BC into segments of 8 and 6 cm at point D throughout this process. The key concepts are the segment relationships, tangent properties, semiperimeter, and area formulas, all interconnected to solve for the unknown side lengths. Now, let's examine the key idea here. When we have a quadrilateral that circumscribes a circle, the opposite sides of this quadrilateral subtend supplementary angles at the center of the circle. In other words, the angles add up to 180 degrees. Similarly, we can prove that the angles BOC and DOA sum to 180 degrees as well. From this, it follows that AOB plus COD equals 180 degrees. This leads us to the conclusion that the sum of these angles, 1, 2, 5, and 6, equals 180 degrees. If we multiply and rearrange these, we see that twice the sum of 1 and 2, plus twice the sum of 5 and 6, equals 360 degrees. Breaking that down further, we get the sum of all these angles, 1 through 8, adding up to 360 degrees. Notice that we also find relationships like 2 equals 3, 4 equals 5, and 6 equals 7, which help us establish symmetry in the angles around the circle. Now, focusing on the triangles delta-OP and delta-OAs, we see they are congruent by the side-side-side condition. Because AP equals AS, both are tangents from the same point, and OP equals OS, which are radii of the circle, and OA is common to both. These triangles are indeed congruent. And this congruence helps us conclude that the angles POA and AOS are equal. By connecting all these points, we reinforce the idea that the opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the circle's center, tying everything back to the overall geometric properties we've been exploring.